It's a real pleasure for me to be in Israel. Being Jewish, it's my pride for this country. And also a real pleasure to be at Technion. I really appreciated performance of Iron Dome, and I think it was done mostly by Technion people. And I hope it will go the same way in the future. I want to start with another talk. I won't be presenting it. Just want to tell you that I was hesitant. It's a very new work. I will be presenting it on Tuesday at Weizmann. It is based on two recent Nature papers. You see both here. It's really recent. It was just published a couple of weeks ago. It's about extremely strong fields. In a sense, it is a realization of a transistor. This is the almost schematic of a transistor, but based on a wideband dielectric, silica, which is controlled the same way as semiconductor are controlled, ultra-fast way, reversibly without damage. And the time of it, the working cycle is less than 1 femtosecond, actually half femtosecond. But I won't be talking about it. I had to choose. I will be talking probably tomorrow, a schedule about the spacer. So spacer would be a very small part of my talk today. Again, I apologize. I'm under very strong jet lag. I've been to France, then I moved to Taiwan. From Taiwan, I moved home for a short time. Then I moved to California. From California, I moved here coming through Atlanta without going home. So my wife suggested me to come to the airport. I barely convinced her not to. Because she is, in contrast to me, only 3/4 Jewish. She is 1/4 Hungarian, and that part that was scaring me. But hopefully, I still have go on my way back, because on my way back, I'm going to Philadelphia the same way through Atlanta without coming home. Still one step to go. This is the contents of my talk. You can look at the highlighted part. It will be the current part, and the unhighlighted part what to show. It's a lot of material to go, so I will start with brief introduction, which has some relation to plasmonics. What mentioned today, it's a cloaking. It shows how important is fundamental physics. It's widely discussed. Nobody knows that cloaking a macroscopic body contradicts fundamental relativity, relativistic causality. It's very simple to show you. At one slide, I'll show you. So cloaking means that wave going around the body and wave going in vacuum acquire the same phase. And they acquire the same phase because this wave goes faster than speed of light. For phase velocity, it is allowed, but requires a metal. If you don't talk even about loss in this metal, now I'm sending a short pulse. And pulse is smaller than the size of the body. It's microscopic. If it's a macroscopic, even microscopic body is not a problem. So I'm sending a short pulse. Now pulse goes around, and the causality tells you that transfer of any material quantity or transferring information cannot occur faster than the speed of light, so this packet should be retarded. And you see that there's something cloaked. You don't see inside, but it's not required. Radar also does not see inside the plane. It doesn't prevent you from shooting this plane. Former officer, I know how to do it. So the condition, this is retardation of the pulse. Express, it's a constant, another one is radius of the body, wavelength, period of the light is much greater than period of the light for macroscopic body. So cloak is easily breakable for short pulses. So for meter body, the retardation would be 1,000,000 times period of the oscillation. It's easily detectable with short pulses, and as you know, all radars are short pulses, specifically for this reason. So you cannot protect yourself at one frequency. Now going to plasmonics. So fundamental to understand. So important to understand fundamentals. I'll start with fundamental. Plasmonics is about concentration of optical energy on a scale. And one may think naively, but certainly many people do, that the best concentration are done with best material. And I can spend money and buy 2 ideal mirrors. I can build Fabry-Perot resonator. The maximum boundary condition tell me that the electric field, the surface must be 0. And the other surface must be 0 at maximum somewhere inside. And this length cannot be shorter than half wavelength. So you cannot constrain better than half wavelengths in space. And this is a theorem. We can break it if you sacrifice ideality. If you allow some loss, and actually it is not a big loss, if you take a real metal and size much smaller than that, about 50 times smaller, less than skin depth. And skin depth for all optical up to terahertz of 1 electron metals is 25 nanometers. Then the electromagnetic field is wave incident vertically penetrates inside. Its force for electrons displaces them, restoring force is electrostatic force. The oscillations of these electrons called surface plasmon. At dipole field of the surface plasmon outside create enhanced field is enhanced by a quality factor of this oscillation, which is about 100 for silver, 10 to 100 for gold. So it's actually big enhancement. It's shown for gold, the factor of 10 in the field, 100 in intensity. All application plasmonics are based on the fact that a significant enhancement of the field, it's electric field, it's not electromagnetic oscillation, it's electromechanical oscillation. But who cares? Because most transitions, whatever we need, most processes are due to dipole interaction. It's only sensitive to electric component and it's blind to magnetic component. So it's okay. So we can concentrate optical energy, not electromagnetic, but optical energy. Now about spectral part of this. We know spatial part. So few nanometers, no objection to concentrate. If you have money to buy gold. It's not that expensive in small amounts. This is it's a bit older, a bit younger than Mayer cited. It's 2,000 years old. It is Roman nanotechnology. It's really nanotechnology. This Lycurgus cup contains nanoparticle of gold. Is precisely timed due to scene that is known when it happened. So we know how old it is. The color, it has dual color. It's dichroic. In the reflection, it is green. It is a color of resonance. And what is left is purple. Purple is the color that Mayer showed you, what you see looking at the suspension of gold. This color has nothing to do with color of gold. It is a plasmonic color. Color of gold is D-band electron transitions, localized transitions. It's not nanometric localized as plasmons. It has nothing to do with color. This is very clear for silver, which is colorless, indivisible. And this is nanocrystals of silver on a dark field optical microscope produce all colors in all visible region, depending on polarization and shape. And if you want to precisely relate the color to the shape, these are shapes, these are gold particles, the colors they produce. And if it were a lecture to our students, I would ask them, I love to ask this question, what is polarization for this particle? So if students are here, they may think on the question and tell me after the answer. To get rid of anisotropic response, one of the most useful nanoparticle, nanosystem is a nanoshell whose frequency depends on thickness. The thinner shell of metal over dielectric, the redder is frequency of the main resonance. And there's a spectra of these nanoshells for different thickness of the metal shell. And for 5 nanometer shell at about a few tenths of nanometer diameter, the absorption is very strong. It goes to near infrared. This is a wonderful transparent region for everything except for this particle. Therefore, it is used for cancer treatment. It's really used for cancer treatment. It's stage 4 clinical trial. Naomi Hallas runs it. This is the first publication on this subject. So I won't be talking about this, but of course, being human for me, treating cancer is an important thing. Being human also has enjoyed these colors. It's La Sainte-Chapelle de Paris, my favorite place to go and to listen to music in the evening. Also enjoy these colors. These colors are variable colors because they depend on angle which you look at it. And this is place illuminated by setting sun. At an oblique angle, you see scattered light. It is color of blood. This was desire of king that built it. This king is Saint Louis, famous. He was a very religious king. He wanted to find Holy Grail, put it in the milk. He didn't get Holy Grail, but the color of Christ's blood, he wanted to reproduce in the windows. He did. Not him personally, but he found artisans who did it. These colors are plasmonic. Therefore, there are no pigments that survived 1,000 years by now, and will survive many more. And they survived a few wars. French were good to removing them. So we know now the spectral, the spatial. I want to comment a bit more on spatial properties of surface plasmons. They have remarkable property. If you take a random system or system with any singularities, plasmons tend to localize on them and get greatly enhanced. So this is local field for fractal cluster of silver, shown over the projection of the cluster. This is a point when this field goes above average, above external field by a factor of 300. It means that intensity goes up by a factor of 300, give me 10 to the 5th. It's a huge enhancement of intensity. It would give you Raman, very strong Raman. It does give you very strong Raman. So why it happens? This random picture of enhancement of dark and bright spots, also known as conventional optics, is a normal picture of speckles. And the speckles that I took from my green laser pointer. So it shows also bright and dark spots, but they're remarkably different from plasmonic spots. You see they're more or less uniform, fluctuation of maximum intensity by a factor of 2. And every separation also is clearly seen. This diffraction determined. There is no diffraction here. Surface plasmons, these are localized plasmons. They don't have wavelengths. They're localized at the minimum scale. And the intensity enhancement is due to both resonance and nanofocusing. So one point has a random concentration because several nanofoci coincide and give you this huge enhancement. This is not only theory, was perfectly found experimental. The experimental picture is so beautiful that it's not worse than theory. I'm very much surprised, but this is true. Normal experimentals tell you, oh, we don't have enough resolution. No, it looks as good in theory. This is sharp spots and dark background. You can, this is hot spots in a sense in natural system, colloidal silver. You can engineer them. And you can engineer them, interesting, quite large particles. It's not easy. The radiation rate is proportional to the amount of the metal for small particle. And this, by the way, the reason the surface plasmons are localized, they live at the surface, they do not emit much energy because they're very small. The very small amount of metal that participates in them. In this case, the small is better. Size does matter. Small is better in plasmonics. So when it is about big particles, you need to engineer hot spots. And it can be engineered if you suppress radiation, and you suppress using phonoresonances. Name of the first actor, phon, is a coincidence. This is Henschel. In this case, the brightness of hot spots is about factor of 100 in the field and 10,000 in intensity. It's as good a hot spot of a small particle. But it's in a big one. You can engineer it and put the shape you want, the place you want. Top down. This is another system that I introduced. It's called a self-similar nanolens. It contains several progressively decreasing in size nanoparticles, as simple as spheres, and they transfer intensity and corresponding enhanced field. You go from larger to smaller, doing the same step every time, so it's self-similar. Even for 3 of them, the enhanced field by a factor of 1,000 in theory, and it was experimental observed. Second part of my talk, I will show you the one experimental result. Let me briefly summarize. Plasmonics is simple, and it's good. It allows you very simple scaling. Can show the plasmonic quality factor, which shows how many times field is enhanced. And also, of course, it is frequency of the resonance divided by double relaxation rate for the amplitude, or approximately is minus a negative real part of an imaginary part of the electric function of the metal, is from 10 to 100 for real metals. It tends to be 100 for silver or for gold in the red. Relative rate of enhancement for the field, for say have a dipolar molecule emitting close to the surface of the metal, the emission rate will be enhanced by a factor of q squared. It goes with the field. And so excitation of this nanoparticle, surface enhanced Raman scattering, contains both processes, so it's enhanced by a factor q to the 4. You can go, it's easy to understand how every linear and nonlinear phenomenon is enhanced. Remarkably, none of them depends on radius. It's not really nanofocusing. Nanofocusing takes big energy and you focus at a small spot. It is not the case here. It's a resonance. It's localized resonance. It's insensitive to radius. So you can take any nanoparticle, any size, and give you the same enhancement. However, radius sometimes does matter. As I mentioned, the rate of radiation, emission rate, depends on radius. In free space, and also depends in the mode. So emission rate in the mode is quality factor of this mode. We give you how strong is the mode, divided by its volume. And this comes from density of states, a density of energy also. So this is how it enhanced temporally, this is how it enhanced spatially. If you look with respect to free photons, radiation of 3 photons proportional to the frequency, so inversely divided, this factor is proportional to lambda cube, is dimensionless factor called Purcell factor. This is true for emission into the mode. This one, that is of paramount importance for spacer. Spacer is emission into mode, plasmonic mode, of a local dipole emitter. And this is exactly why spacers work, because emission into spacer mode is much stronger for smaller particles. About temporal part of plasmonics. I talk about frequency, about space twice, now about temporal dependence. How long do plasmons live? This is lifetime, decay of energy of population. Polarization lives twice longer. For surface plasmons, you can show it doesn't depend on the shape. I mean, it depends on shape. Let me make it precise. It does depend on size for small particles strictly. It doesn't depend on shape except through frequency of the mode. So only frequency of the mode matters. Shape and polarization define frequency. If you know frequency, this is a decay rate. It's a function of frequency. And in the whole optical region when plasmon exists, say for this for silver, it is from about 10 femtosecond to about 60, 70 femtosecond. It is a sweet interval, sweet region when there are very good ultrafast method. And this is required. This is very many electronic processes and molecular even process occur for fast relaxation. It goes about 100 femtoseconds. What is the fastest time plasmonic system can react? It has nothing to do with relaxation time. Fastest time is determined by bandwidth. Is inverse bandwidth always for any linear system. It's a result of beating of different spectral components, as we know, when we do Fourier expansion. And for plasmon, say on silver, it's about 4 electron volt of available bandwidth. So the corresponding reaction time comes to about a few 100 femtoseconds. However, if you add aluminum to the mix, aluminum has plasmon frequency 9 electron volts, so you shorten response time to about 100 at a second. And this is a limit to what any material system can do in a visible or ultraviolet region. This is how fast can be plasmonic responses. What of this was experimentally investigated and theory was tested? Almost everything. So I'll show you a picture when you will see both spatial behavior and the temporal behavior for rough silver, it is not really rough. It is actually a surface of monocrystal silver, but it has steps of growth shown here. And the steps of growth are rough, they're not regular, and they localize plasmons. When you excite them with laser pulse, you see these hot spots which I was talking about. They really look like hot spots. This is a bar from this, how it was measured. Of course, you cannot measure it in far field. It's measured in far field. So it is not optical measurements, it's electronic measurements. It's photoelectron emission, or PM microscope. PM measured it to make temporal, and I can tell you that the energy of the photon for 400 nanometer exciting blue radiation is 3 electron volt, and work function for silver is higher than that. So one photon cannot emit electrons. So all emission here is a 2-photon emission. If you excite with 2 pulses, there will be events that emission is due to absorption of 1 quantum from the first pulse and 2nd quantum from the 2nd pulse. There will be interference depending on phase of that oscillation acquires between them. When you change the delay, this interference changes from constructive to destructive, and you will see it as a blinking hotspots. So this movie shows you stroboscopic measurements as a function of delay shown here in units of 250 attoseconds, so quarter optical period shift. And initially it starts with 0 delay, so at the first moment you see simple interference. There is no information about material system. This information appears when they separate by more than their width. At this now, you see like this plasma peaks start blinking, and this blinking reflects their blinking in real time. You also can think about this as a coherent control. You see these very close spots. One goes up, second goes down because they have different frequencies. These modes accumulate different phase, and we control them. And also you can measure directly how fast plasmons react. They do react with femtosecond times. And this is what corresponds to the bandwidth of these resonances. One of the phenomena that turned out to be very important in both technology and is also important for fundamentally is the concept of adiabatic nanofocusing, adiabatic concentration that I introduced in 2004. It's about 9 years ago already, time flying. Idea is that you send polaritongs, which are propagating plasmons along the surface of the cone, and the cone is with small angle. They are converging adiabatically. Adiabaticity prevents the reflection. And small size prevents also scattering. Polaritons do not emit by themselves the dark excitation. So that is dark mode that is going. It repeats, it adiabatically follows the shape and concentrates. That shows you the calculated picture of the fields. And they enhance by a factor of about 30, I mean that intensity in this experiment, in this specific calculation, when it's compression to about 10 nanometers, goes up by a factor of about 1,000. This is how it occurs. It's proportional to the radius to the power of 3/2, the 3-dimensional compression. This is calculated picture of compression. You really create a hot spot at the end. Advantage of adiabatic compression, it is not resonant mechanism. It's extremely wide band. It can be extremely fast. And I'll show you experiments as we go. This is the first experiment that simply shows mechanism as conceptually introduced works. It is a adiabatic concentrator, which is a wedge actually. It's not a cone. It's a flat at the planar system. But at the end, it looks like a cone. The polaritons launch from the launch pad. They propagate along this system. They're dark. It is observation by a NSOM, near-field scanning optical microscope. There is nothing at the surface. These polaritons propagate between metal and underlying dielectric, and then they wrap around, form the compressing mode, get compressed, and we transform that to wire 10 micron. They propagate along 10 micron. You see there is no beatings, no fringes, no back reflection. They go one way. So system does work without reflections. And this is measured phase, and phase exactly as predicted. The signs are as predicted for the mode. And you can also measure the throughput, making such two compressors next to each other, and throughput in this specific experiment was 25% in intensity. It means to the middle it delivers experimentally 50% of energy from the laser, with all losses on the way, including coupling losses. So it's a remarkably efficient system. This is localization measured for three-dimensional cone, and it is used in microscopy. The full width of half maximum over sharp edge is 22 nanometers, so this is resolution achieved. Today, the best resolution achieved by this method is 7 nanometers. Not only you can constrain the space, as I told you, it is very wide band, so it can be constrained in time. It was done using all the methods developed in ultrafast optics. This is restored shape of the pulse at the end. It's red is its envelope. This is the blue is the temporal phase. It's a very flat, which is good. And the width is a 10 femtosecond. It's a 10 femtosecond pulse delivered to about 10 nanometer area. It's a perfect probe for any ultrafast localized process. Nanolenses. This is what nanolens I mentioned. It is nanolens of several nanospheres of silver, and actually it doesn't matter. And this is from gold. Done experimental, gold is better, doesn't oxidize. These nanospheres can be any order, in fact. This is an unusual order, and it enhances, gold enhances less than silver. Intensity, a field by 100 times, but 10,000 times enhancement of intensity is 10 to the 8, 10 to the 9 enhancement of Raman. That's exactly what measured. This is a Raman experiment, is the source signal. And this is from methanol. Methanol does not show any source. This was known used as the for calibration. It's a 10. This thing is dying. This is 10 mole of methanol give the same Raman as, let me read, is 10 minus 8 methanol of adenine. Adenine gives source. So it is by Berrie 10 to the 9 enhancement of Raman from these nanospheres. Now, 10 to 9 is not record, of course. What is record here is cleanliness. This 3 nanospheres is not a big cluster. This is Raman, this is the background experiment. This is background. It's absent. I mean, there is no background. This nanolens is obtained by ablation. No chemistry ever touched them. Therefore, there's no background. There's no chemicals involved. It's another experiment done very recently, 2012. Lukasz Novotny and his group used this nanolens, putting them at the cone of the ensome. So this is cone. This is actually not a cone ensome. This is a silica cone. This is the only working part of the system. But some people would also put it on the metal. Doesn't matter. That's what works. The 3 nanospheres give you very high resolution. You have 15 nanometer resolution. And you look at this 15 nanometer taking object with 0 size, a molecule. So you see single molecules easily. And the resolution is close to the record. This is the spacer. I will be talking about the spacer tomorrow. I won't be talking much today, but I mentioned a few things. So spacer is a nanoplasmonic counterpart of the laser. You replace photon by plasmons. And plasmons, localized plasmons don't have wavelengths, as I told you. They always localize at the size of the system, so can be localized very tightly. Localizing very tightly, they produce very high field for one quantum. This is for one plasmon. This is nanoshell of silver, and produces field 10 to the 6 volt per centimeter, megavolt per centimeter. One quantum is for laser unthinkable. It's too high. It gives you extremely high feedback. So spacer can work at a few plasmons per mode. It does work. The number of spacers done. So otherwise, it works like a laser. You add gain medium. You excite gain medium. It relaxes the working states, exciton for the sake of argument. And you tune it to the plasmons. So one plasmon is created by spontaneous emission into this mode. And as soon created, its field is now here. It penetrates the gain medium, causes more and more. And if the rate of emission is higher than the rate of decay, you have an avalanche. And this avalanche, normally people stop. Avalanche is the beginning. It means that this is instability. It's a phase transition, and the second order phase transition in equilibrium, and this phase transition leads to establishment of a new phase. This phase is phasing. This phase is characterized by a phase. It's like a crystal forming. No, it's first order phase transition, but crystal forms from solution in randomly false order, or magnetic forms order. You have randomly established direction of magnetization, second order transition, and so on and so on. So this is this type of transition. One of the, this is a spacer made of gallium nitride, gallium nitride, gain medium, so indium gallium nitride is the emitter. And this is metal is silver, is a epitaxial silver. Mode is localized mostly between them and also in indium gallium nitride. That creates a feedback. This so-called LL line, anybody who works with lasers can appreciate it. This is a jump when generation starts. When you're going from spontaneous emission to amplified spontaneous emission, the simulated emission. And this is by theory both, and by experiment is a straight line. And the reason straight line is the more you pump, the highest rate of simulated emission. It never saturates until you melt it. So somehow you break it. This is how spectral establishes spacing, creates a very narrow line, very unusual for the fluorescence of a nanoscopic body, but it's a very narrow line. It becomes narrow and narrow as you pump, like Shavrov-Towns predict. Precisely this way. This is another remarkable thing. This is second order correlation function of intensity. Before spacing, it's a Gaussian statistics. You have this Brown-Twiss maximum in the middle. As soon as spacing starts, there is nothing here. It's straight line as should be for any saturated generation. So it does behave like a laser, though the size, diameter is 30 nanometers of the system. Why spacer is important? There's another, not only it's a very bright, almost unlimited brightness of label. You can use in nanomedicine, and every label you use, you can excite it, but very easily saturates. So brightness will be limited. This thing has unlimited brightness. Again, until you melt the metal. But there's another reason why it is important. And this reason are computations. Spacer is an amplifier. And you can put in the mode it will amplify. An amplifier is important because it's a part of logic, digital logic. So it can work as a digital amplifier. The only question is, why do we need another digital amplifier? It's not a trivial question. This is transistor that runs my computer. Two actually of them. This is a cross-section through the chip, courtesy of Intel. The transistor runs. This transistor can run at 100 gigahertz. And the chip runs at 3 gigahertz. And it doesn't go any faster. And therefore, when new transistor is introduced, this is actually from original Intel presentation. If you look what they're presenting, it's very interesting. They're presenting size, 3228 nanometers, and MOS technology. This is the drive current, first mentioned how much current it can drive from source to drain, and the risk of current. That defines how economical is the processor. There is no time here. They don't care about frequency of the transistor. So why they don't care? If they were talk I would give to students, I would say, I love to do, I would ask why. Why they don't care about speed of the transistors? And it doesn't matter at all. And the answer is shown on this cross-section. You do not see transistors here. There are speckles at the bottom. You barely can see the thinner, the thinnest wires. All the rest of this are copper wiring. And this is why processor is slow. This drive current needs to charge the wire to the 0.9 volt, which is the potential given by semiconductor. And this time depends on the capacity of the wire. You cannot change much. And drive current. It's inversely proportional to drive current. And for drive current determines how fast is this system. Can we change it ever? If you use electrostatic approach like we use for transistors, no. Everything would be the same. We can change, we can engineer at 10% better. Not much, actually. Even if it replaces silicon technologies, unlikely, but direct gap semiconductors won't change much. Wire will be there. You need to change principle. You need, instead of electrostatic coupling, use a wave coupling. Send a short pulse, a polariton. But transistors are not sensitive to polaritons. And this is the next generation transistor would give you exactly the same speed. It will be just more economical. You need all optical processing. You need a device which is sensitive to injection of quantum amplifier. And spacer is a quantum amplifier. So this is a grand challenge. Because it's not easy to replace. Transistors are perfectly suited for processors because there are two of them that don't consume much energy when they are not switching and so on. Spacer does have this property. So it should be, architecture should be completely rethought. Now I'm going to application of plasmonics as I promised. This is a list of them, pretty long list. So, for this thing, do you have another one? I have actually somewhere in my backpack because the thing is dying. This should also work. It doesn't. It does not. So the first application, ultrasensitive and express sensing, based on the fact of the high local fields. You excite molecule with a high field, you get stronger response. This is a review of Van Dyne's group by sensing with plasmonics nanosensors. So I would refer to it. Oh, thank you so much. Near-field scanning microscopy or nanoscopy and somosnom, which is the same, I will briefly mention. Nanantennas, we'll mention today many times how you use them, in particular use extraction of light from LEDs and lasers, and I will give one example as I go. Also, you use in solar cells. So some solar cells don't have them, some do. Again, solar cells is a different proposition. I would somewhat digress with respect to what Eli would say. Problem of solar technology is not semiconductors. It's not efficiency. Problem of solar technology are environmentalists. Solar technology is unbelievably damaging for environment. It kills everything underneath because it doesn't allow light. You put in the desert. Desert is not a desert, it's an ecosystem. And you kill everything there. Number one. Number two, you saw the area, and those are connected by copper wires. So copper soon will be as expensive as gold. Coming to this point. Advantage of other technologies, normal thermal generation, I guess becomes very cheap in the United States. Unbelievably cheap. Very difficult to compete with this. It's very concentrated, both nuclear and gas. And my favorite country, for the reason I don't know, maybe for food, is France. It has cleanest air, and they use electricity for most of the energy. It's nuclear generated. So I don't know about solar, but as a physical system, it's important. Also, there are very bright diodes which are needed for lighting. If you even use the old technology, because the semiconductor lighting produce light, that by itself would give enormous decrease of amount of CO2 in the atmosphere. Though again, I'm not convinced that this CO2 creates the global warming. That may be methane. Another application that is real-time application, they use basically every day, use these probes and labels. They're very good scatterers. So put them on membranes, they put them anywhere. You can see transport with gold nanoparticles. And gold nanospheres are not biologically damaging to any extent. They are allowed by FDA for use in humans. Nanoplasmonic-based immunoassays tests. This is the biggest scale application of plasmonics. You can go to any drugstore, and if you're a woman or you're a good husband, you can buy your wife a pregnancy test. And this is the most important phenomenon for humankind. We can do whatever we want, but we need to be born first. And for that, somebody needs to get pregnant. So the pregnancy test is important, and also other tests. In particular, PSA tests, so men will not feel themselves abandoned, that they go regularly. It's done also using plasmonic tests if you want it fast. Heart attack test, troponin test. This is one of the most important because, you know, all we under God. And HIV test. We should avoid this, but in trials, it has enough sensitivity to measure even HIV. Next perspective is generation of EUV and XUV pulses. This is somewhat problematic. What is in practice now is stage 4 clinical trial. As I mentioned, it is cancer treatment using near-infrared light and gold nanoshells to sensitize tumors. Otherwise, nothing in the body absorbs SUV. Sensing detection. I will give you a few examples. This is what you buy in the drugstore. This is how inside fundamentally works pregnancy tests and all other tests. So you add liquid you want to analyze. It's chromatographic paper, start diffusing. Here is a strip that contains antibodies against what you want to measure. And this so-called primary antibodies. So they would capture this antigen. In this case of pregnancy, it's called HCG. And then you add developer, and developer are gold nanospheres containing secondary antibodies against the same compound, and they couple to the antigen again, and they bring nanospheres together, forming dense layer of gold. And you saw the color of dense layer of gold. It is purple, bright red. There's absolutely no mistakes when it works. Otherwise, in solution, it is vaguely green. So it's a very high contrast test. Works perfectly well. You can violate all rules and still will work. And you can use for other immunological tests. There is another version of the same test. I won't comment it, for I don't have time. But it's based on the shift of frequency of plasmonic resonances. It's pretty sensitive to go basically to the limit that you need to detect HIV. And in practical medicine, there is nothing more sensitive is required. This work is not finished. This was in progress. I didn't hear lately about this. It's a measuring glucose continuously in the blood. Extremely important. In the US, about 20 million have diabetes, including myself. In particular, Ashkenazi Jews, unfortunately, half of them have diabetes. Blacks have diabetes. And many of them are poor, they even don't know. And diabetes is a killer, killed my father. So it's an important thing to measure diabetes. Another region of measurements, you may not, healthy people who work long hours, pilots, for example, blood sugar goes down, they can crash the plane, which happened. French did, though I suspect alcohol was a factor. Another important region of sensing is immediate express sensing of hydrogen. So eventually, we will have hydrogen cars. They will be extremely clean if cleanly produce hydrogen. It's another problem. But imagine we can do it, but we need to sense hydrogen. Otherwise, you cannot use it. That will be the fate of Ginsburg. Airship. This, you can use palladium-based. Palladium is plasmonic metal sensor. Palladium expands, changing plasmonic frequency, is very sensitive. I saw myself the sensor work in Gießen lab. It's about 3 seconds before it gives long signal. So this is what is required. So palladium sensors, plasmonic palladium sensor are installed in all hydrogen cars. Now the most common sensor used in medicine and environmental monitoring is so-called biocore sensor. So biocore sensor is based on surface plasmon polarity ion, which are excited through heavy glass. Heavy glass has low phase velocity, high K, and having high K, it matches perfectly to polarity ions on the upper surface, which is surface with water or vacuum, if you want, low polarizability surface. So you compensate by refractive index for higher speed of propagation in the vacuum. So here, if you look at the picture of fields below and above the metal surface, they're perfectly phase matched. Therefore, energy from the wave goes to polarity ions, but it happens only at one angle. This is called Kretschmann angle, which is inside the cone of total internal reflection. However, if we change condition of the upper surface, within the layer of about 100 nanometers from the surface where all energy is, putting molecules there, that will shift the frequency and shift the angle. So this is a red curve, give us Kretschmann resonance, a function of angle, when there is nothing in the upper surfaces, and the blue gives you the similar curve when there is one monolayer of protein. And this is a significant shift, much greater than the width. So this test is sensitive enough to detect real immunological reaction occurring in the upper surface. Great advantage is unbelievably cheap. This microscope slide with evaporated gold costs about $1. They sell it for probably $100 to us. The time of measurement a few minutes, so you can see reaction in real time. If you go to something more interesting, more developed, it is spatial spectral imaging. It is done with 7 nanometer resolution. It is a step from silica to silicon. It's a very sharp step, and what you see 7 nanometer steps here, and the brightness of the line is the silicon line. So you see the trench here, silicon trench. So by Raman, so it measures Raman scattering, surface that has Raman scattering. It is based on adiabatic compression. It's a very sensitive probe, because it requires very high enhancement. It is done with spectral and spatial resolution. To my knowledge, this is today the only one that can do it. A continuing plasmonic nanoscopy is another pleasure for me to introduce device from Israel. It is from Nanoplasmonics, which is Jerusalem company by Aaron Lewis. The sensor here is a metal nanoparticle at the end of capillary, which is plasmonic enhancer. This is a microscope you can measure from top to bottom. This is a picture of human cell with sub-wavelength resolution, and it's a living human cell, so it doesn't have to be fixed. It is in the real water, or physiological solution is living. It's a skin cell. You can go to high resolution. You can get also a Raman picture with a simply sharp cone. And what's shown here is a nanotube of a carbon nanotube, which looks like it is uniform. But if you take a Raman spectra at many points, you see how strongly the spectra changes. This tube actually is non-uniform and changes chirality. And this tube was supposed to be used as transistors. But this one cannot be used. It should be completely clean. If one chirality, then you can, and be semiconductor, they can bias it. And this changes many times from semiconductor to metal. This is as an example of using for nanoscopy. This is Raman nanoscopy. You can use for usual nanoscopy if you take a nanosphere at the end of glass, and you can see a single molecule here. So this from Sandagdar group work. You can study multiple single molecules with polarization. This is polarization sensitive approach. It's somewhat similar to adiabatic compression. I have normal SNOM tip, it's aperture SNOM, and there is nano cone grown on it. So how it works is a different story. It can work as antenna, can work as adiabatic compressor. You can see single molecule along with the polarization, which will tell direction of the dipole of this molecule. And final example is a picture. This is the atomic force microscope picture of a tentacle of a cell. It's called oligodendrocyte. And you see the white fiber here. You see it in the atomic force microscope. It's a good resolution. I don't know. It's probably 10 nanometer. If you use the same, exactly same object, you can see the same features which you see at the surface. You can use optical microscope. You see something you do not see at atomic force microscope. With a thin fiber underneath, which is inside, you do not see it from the surface. But optics penetrates, and this fiber is a skeleton keeping this dendrocyte together. This picture, I said, repeats the same. It's a measurement silicon interface, so I won't be commenting on it. Don't have it. Plasmonic nanoantennas. Among nanoantennas, I will consider two of them. This one is high importance. Most long-term information storage is still on magnetic memory. It is not yet on flash memory. Though I would prefer flash memory personally. My computer has no flash memory, but it's not archive storage. Archive storage certainly is magnetic today, will be magnetic for the time being. Problem of high density magnetic recording is if you use a soft magnetic as used today, then you cannot remagnetize it with a normal head. If you use a hard magnetic, you try to make a hard head with high field, it's a lot of energy, it's a lot of heat, it's slower. So can we use a normal head, soft head, with the hard magnetic? And the idea is to use heat-assisted recording, to heat magnetic above Curie point. And when it cools, it will remember the field. But you need to heat it selectively at the spot of the same size at the right magnetic bit. And this is tens of nanometers, which is desired. So you need a plasmonic source of heat. The plasmonic source of heat are plasmons at the metal. They heat the metal, heat whatever is around the metal. This one uses the conversion from running wave to something that looks at nanoparticle, but if you look at the electron micrograph, this is antenna, and this is a adiabatic compressor at the end of it. And it does work. So they irradiate this antenna, it transfers excitation to this adiabatic compressor. The compressor creates the field at the end. It's a non-resonant effect, which is good. You don't have to tune it. And then you hit the magnetic and you leave the recording, which is about 70 nanometer wide. A length is determined by bandwidth of the head. So it works. The only problem, it is not yet industrial, as I know from people working on it. And I suspect, they won't tell me the reason. I suspect the reason, problem of alignment of them. So the magnetic part and the electric part should be the same spot. And this is 10 nanometer spot. But if they can solve this problem of alignment, then the adiabatic compression, of course, give you a ideal way to deliver energy to the region you want. This is another way of enhancement. This is plasmonically enhanced photodetector. And this photodetector is a nanoscale detector. It's germanium nanocrystal. And plasmonic part is this dipole antenna. Those are leads which do not participate. This is electron micrograph. It enhances the response of the small crystal by a factor, almost by 2 orders of magnitude. And I always ask students, why do we have to go through such pain to make a small crystal that increases cross-section by an antenna? Why not to take a big crystal? No students here. Okay. The answer is the noise comes with the volume of the crystal, because noise is spontaneous generation of electron-hole pairs in the whole bulk. And the smaller crystal, the smaller noise, by photocurrent absorption. If you concentrate the energy, that depends on the energy you deliver. And it does depend on size, and this idea, enhancement. This is another practical important device. So there are quantum cascade lasers, and nothing in the infrared, mid-infrared is more efficient. The problem is that quantum cascade stack of quantum wells is nanoscopic. It doesn't deliver any angular collimation. And lasers should be collimated, much better. So how it is done, they use a plasmonic collimator that transforms that near field of the quantum cascade laser into a focused beam, and a focused collimated beam, and it's done with very minimum losses. So this is one of them calculated, and the second, this is measured, this calculated, barely distinguishable. Works exceedingly well. Done by Kapasa, of course. I'm coming to the end. Let me give you conclusions. You can actually read them. So nanoplasmonics is huge. It's industrial. It works very well. And why it works? Because it's exceedingly simple. Metals do all the job. It's stable. especially when you do it without much relying on resonances. It's very stable if you use adiabatic compression, for example. You can use resonances, then they need to control the shape. Also works. It works very well when you know why you do this. It works very well for cancer treatment, somewhere should be. And cancer treatment, you use the simplest thing, production of heat in the nanoshells. The only thing you do, you put the cross-section when you want, when the tissues do not absorb. And eventually, if I go to my favorite, of course, this is a spacer. It's extremely bright label. You can use it as a source of energy of nanoscale for any application, including source. You can generate field and enhance it by the same metal of the spacer. But most importantly, maybe our century of information. A lot of energy, by the way, that is so difficult to produce, is now spent by data banks, Google and the like, and it will be more and more and more. So we need to make computing faster to make it more efficient. So we can process immediately and stop it, not spend any energy. And if you can do spacer, it would be good. And I didn't mention another part of spacer, maybe in Israel I should. God forbid there is a nuclear conflict. Everything that runs by computer will be dead. Because if you take a MOSFET, it is a capacitor. You make one hole. A hole will be made either by an energetic proton or energetic gamma quantum. Oh, neutrons also can do it if there's a bad luck. And so in the case of nuclear explosion, nuclear fallout, you cannot even send the robot unless it makes on vacuum tubes. The history of Fukushima told, and before the Chernobyl, you have to send people to the hot zone because robots will not do the job. A spacer as a metal is absolutely insensitive, is as least insensitive as ever possible to radiation. The metal has what is called glacial degradation. You damage it with neutrons. It expands, but very slowly. In reactor, it works for 30, 50 years. So it would be very desirable. Finally, US military produced the first MURI at a big call for proposal for space. Okay, I finished. Thank you. We're happy to answer questions.